In the Advanced Laser Diagnostic Lab, we develop novel strategies to overcome existing limitations of combustion diagnostics. The corrugated picosecond Raman spectroscopy temporally separates the Raman signal from soot incandescence and laser-induced fluorescence, enabling interference-free Raman measurements in mildly sooting flames. The Hydro, our hyperspectral 2D Raman analyzer, allows 2D Raman measurements of temperature in major species in high-pressure, non-sooting methane air flames. It also allows for high-precision 1D Raman measurements at 10 kHz. We have extended interferometric Rayleigh scattering velocimetry from point-to-line measurements with our novel design based on a virtually imaged phased array. The diagnostics will be employed to study combustion in small channels and supersonic combustion. In the Combustion and Pyrolysis Chemistry Laboratory, the gasification and pyrolysis of different residues such as biomass and heavy residues from crude oil are investigated. Fractions from various feedstocks can be separated and investigated independently in our different reactor facilities under fixed temperature, pressure, and residence time conditions. In addition, we perform high-fidelity numerical simulations using quantum chemistry, kinetic rate calculations, and molecular dynamics to understand oxidation and pyrolysis in reactive environments. For gas phase systems, we conduct experiments in flames and jet-stirred reactors to understand chemical reaction mechanisms and determine associated thermokinetic parameters related to oxidation of different types of fuels. In addition, we have special reactors for studying catalysis under heterogeneous gas-solid environments. In this lab, we measure the electric field of plasma-assisted flames by a laser technique called EFISH, for electric field-induced second harmonic generation. A methane air flame is ignited in a stagnation flow burner. This flame can be seen here with and without plasma. To measure the electric field, an infrared laser is focused on the flame region, a part of which will be changed into a green beam. The beam's intensity is proportional to the laser irradiance and the electric field squared. This technique can measure the electric field during plasma actuation of the flame, which is crucial for the understanding of plasma chemistry. Welcome to Building 7, our high-hazard H5 classification lab space, where we house most of the larger-scale projects. KAUST was built to Saudi Aramco standards for petrochemical plants. The sophistication of the toxic gas management system is clearly evident on the walls in this corridor. The lab is capable of providing 0.5 kilograms per second of airflow at 45 bar continuously, plus an extensive fuel delivery capability including hydrogen, methane, ammonia, and various liquid fuels. The high bay area, with a ceiling of 12 meters, contains several large, high-pressure experiments. The centerpiece is the high-pressure combustion duct, the center's workhorse for studying canonical flames at pressures relevant to gas turbines and internal combustion engines. Here you see a high-pressure ammonia swirl flame and a part of the laser-based diagnostics being developed to measure a wide range of major and minor species. Also in this lab is the heterogeneous auto-ignition rig, designed to study the combination of chemical and physical delay in the autoignition of real fuels at pressure. This lab also contains the pressure gain combustion rig. This rig is used to investigate an alternative to constant pressure heat addition in gas turbines using constant volume heat addition. This isochoric heat addition results in an increase in stagnation pressure and hence thermodynamic efficiency. We are investigating acoustically resonant deflagration waves using either passive or active valving to demonstrate pressure gain combustion at elevated initial pressures. With the growing interest in hydrogen and ammonia, we are investigating the feasibility of converting a conventional natural gas-fired microgas turbine to an ammonia, hydrogen, or ammonia natural gas-fired gas turbine, measuring both the performance and emissions from a commercial device. In this lab, we have two experiments: the new very high-pressure constant volume combustion spray rig and the Turbulent flame speed rig. The spray rig is designed to handle pressures up to 300 bar to investigate next-generation isobaric combustion using a pre-burn to generate the necessary temperatures. This vessel will also be used to investigate supercritical carbon dioxide oxy-fuel combustion at pressures relevant to the alum cycle. Note, both of these rigs take advantage of the blast-proof control room and can be operated from this room for safety. The second experiment allows for the investigation of chemistry turbulence interactions by measuring turbulent burning velocities at various initial pressures, temperatures, and turbulence intensities. The isotropic turbulence intensity can be controlled via 4 high-speed fans. Using Schlerin imaging, the expanding combustion wavefront can be measured. Here we see a laminar stoichiometric ammonia plus DMM in air flame at 5 bar. From these images, we can calculate unstretched laminar burning velocity as well as Markstein length. The turbulent flame shown is an ammonia flame in oxygen-enriched air at 3 bar. This is the Chemical Kinetics and Laser Sensors Laboratory. The 2 shock tubes are designed to study fuel autoignition chemistry and elementary reaction rates. We can assess pressures beyond 100 bar and wide range of temperatures. Various laser diagnostics ranging from ultraviolet to mid-infrared range are employed to follow the evolution of reactants, intermediates, radicals, and products. Simultaneous end-wall and sidewall high-speed imaging helps investigate inhomogeneous ignition. The laboratory also houses a twin-opposed piston rapid compression machine to investigate fuel autoignition at low temperatures. Laser diagnostics have been used to ascertain the validity of homogeneous core in the RCM. An optical combustion chamber is used to study the occurrence of pre-ignition and supernovae. New laser diagnostics and sensors are designed for specific applications. Recently, a novel difference frequency generation laser system has been constructed to assess the bending vibrational modes of aromatics in the 12 to 15 micrometer wavelength range. Equipped with 7 engine test benches, the research in our internal combustion engine labs is focused on studying novel concepts and technologies to reduce the carbon footprint and pollutants emissions of the transportation sector. Here, our all-metal heavy-duty single-cylinder research engine is used to study the pre-chamber combustion concept as part of the FuelCom 3 project in partnership with Saudi Aramco. Different pre-chamber designs are being tested and evaluated to identify the key geometry features to reduce fuel consumption, NOx, CO, and unburned hydrocarbons emissions. Our testing setup is capable of measuring the engine indicated efficiency and emissions with high accuracy and high precision. The engine is operated in well-controlled conditions, which ensures the reproducibility and repeatability of our experiments. In this project, our ultimate goal is to improve the efficiency of spark ignition engines while reducing emissions to near zero levels. Our labs are also equipped with 4 optical engine test benches. They are designed to allow full optical access into the combustion chamber through an optical piston and liner made of high-purity quartz. Here, our optical heavy-duty single-cylinder research engine is used to study combustion in an optical pre-chamber. High-speed chemiluminescence and a variety of laser diagnostics reveal the physics behind the observed trends and provide detailed data sets for calibration and validation of numerical model. Our ultimate goal is to perform advanced laser diagnostics to study the pre-chamber combustion. This relies on developing new optical techniques and adapting their operation to the engine environment. Using a near-term Grand Challenge grant from KAUST, the center was able to partner with Sustainable Energy Solutions in Utah to bring their cryogenic carbon capture process to the kingdom. Here you see the 3 shipping containers housing the components for this 1 ton per day CO2 capture scale rig. The rig is capturing flue gas from the corrosion rig and removing both water and CO2 with greater than 90% CO2 capture efficiency. Working with SES, we were able to de-risk several components, giving us confidence to move up in scale to a 25 to 30 ton per day facility. Due to the cryogenic process, we are able to simultaneously remove sulfur dioxide and nitrogen dioxide as well as CO2. We are developing novel direct contact cryogenic heat exchangers to improve the thermal effectiveness and hence increasing the overall efficiency.